In this video, we're going to talk about unit impulse function, or simply just impulse function. The unit basically refers to the fact that its coefficient is 1, its value is equal to 1, but most of the time you hear it referred to as just simply impulse function. Let's start with the discrete time. So if we start with the discrete time, unit impulse, that is represented as delta n. That's how we write the unit impulse function. And the definition for unit impulse function is that it is equal to 0 as long as when n is not equal to 0, and is only equal to 1 when n is equal to 1. So let's go ahead and do a plot here. So for example, if we have n on these axes, that basically means this function is going to have a line that comes down at 0 and its magnitude is equal to 1. And that's the Greek letter delta is used to refer to it, and that is definition. Now, we have n here, but you could have any expression in here, and it basically says whatever that expression is equal to 0. Now, why do we have such a function? We have this function because it's very useful to be able to, like if I have another function and I just want to take a sample of it in one given point in time, it's very useful to use this. For example, if I say sum of x of n, but x of n is just a function with all kinds of values from -infinity to infinity, and if I multiply that with an impulse function of delta n, since this is only non-zero, it's only equal to 1 at one point in time, and that is when n is equal to 0, that means this whole function gets reduced to x of 0. And that's called a sifting feature, and that's one of the reasons we are studying impulse functions here. Okay, now let's generalize this just a touch. For example, if we have delta n minus just a constant n0, that means this thing is equal to 0 everywhere, that everywhere when n is not equal to n0, and the only place it's 1 is when n is equal to 0. Okay, so now we can use that in a different way. For example, if we had the same function, summation of n equal to -infinity to infinity, x of n, delta n minus n0. Now we know this is n minus n0. We know this is 1 only in one place, and that one place is when n minus n0 is equal to 0, or in other words, where n is equal to n0. So that allows us to basically say this whole function is basically x of n0. Now, let's do one more example before we walk away from here. So this is kind of useful because I could have somebody gives me a function that, let's say, look like this. 2 in here, this is -1, 0, and maybe -3 at 1, and maybe at 2 is 4. If this is an x of n, and somebody asked me, can you use impulse to write this function? The answer is yeah, we could do that. What all we have to do is basically say there is an impulse function right here. There's an impulse function. Let me get a different color so we can. So there's an impulse function right here. There's an impulse function right here, and there's an impulse function right here. So I can literally write x of n as delta n plus 1, really, right? This is n n0 is -1, so Left, right, n plus 1. And in this case, the magnitude is 2, so there you have it. For this one, they'll basically, the magnitude is minus 3 delta n minus 1. This function is only 1 when n is equal to 1. And then finally, we have plus 4 delta n minus 2. So without an impulse function, we wouldn't have been able to write this function. Now we are able to do that. Now let's go ahead and move on and take a look at the counterpart for this for continuous time. The behavior of impulse function in continuous time, it's very similar to what we just described there. It is also represented as delta t instead of delta n, and of course uses parentheses instead of the square bracket, but the definition is fundamentally the same. It says this is equal to 1 when t is equal to 0. And what we are saying is that all the expression that's within the parentheses is equal to 0. In this case, we just have a t. And it says it's 0 when t is not equal to 0. Once again, we can generalize this, much like we did up there, and say actually the general term is delta t minus t0, where t0 is just some arbitrary positive number or negative number, is equal to 1 when what's inside the parentheses is equal to 0. So t minus t0 is equal to 0, which means t is equal to t0. Otherwise, basically anytime t is not equal to t0, or another for this is not equal to 0, this is equal to 0. Okay. So what do they look like? Well, if I plot these, the delta t basically sits at 0 equal to 1. So this is representative of that. This one is represented, let's say t0 was positive, it would sit here, t0 is here, and the impulse would be sitting in here. This is t-axis. Okay, and it also has the same properties we talked about before. If I were to have an integral, or x of t, some x of t may be some broad from minus infinity to infinity, and delta t dt, that basically says the only time this function is a 1 is when t is equal to 0. Therefore, this whole thing is equal to x of 0. So we're sampling t at 0. Now let's say if you sampling x of t at t equal to 0. So let's say if you want to sample it at another place, much like we did before, we're just going to multiply with the impulse function at a different location, delta t minus t0 dt, and now we have the sample at whatever time we now liked within t0. Okay, so that's called the unit impulse for the discrete time. Now mathematically, and I'll go back and do this so you've seen it, mathematically we need to distinguish between a variable here and the variable of integral. So what we typically do, we replace the t with tau just to create that distinction, and then take a derivative, because t is going from minus infinity to infinity. We don't like to have the same variable and the limits be the same. So they usually write it as x of tau delta tau, or x of tau delta t. Instead of writing it in t, we write it in tau. Okay, so that kind of brings us to the end of this. It's just another function that allows us to more flexibility in what we're representing. So we've talked about delta n for the discrete, and then we have talked about delta t for the continuous. Both of these are called unit impulse function, or in many cases just simply impulse function.